Our goal is to create an AI agent that can accurately jump over obstacles and achieve the highest score possible. We'll use TensorFlow.js, a JavaScript library for training and deploying machine learning models into the browser. We'll start by designing our model architecture. We'll use deep Q-learning and the concept of dueling networks to build a powerful model that can estimate the Q values for different game states. To add some exploration and randomness to our model, we'll implement the noisy dense layer, and this will allow our agents to learn from a more diverse set of experiences and make better decisions. Additionally, we'll incorporate advanced normalization to ensure more stable and reliable training. These techniques help us handle variations in the advantage values, making our model more robust. Once our model is set up, we'll dive into the training process. We'll use an iterative approach where the agent interacts with the game environment, collect experiences, and learn from them to improve its performance. We'll also explore how to load our save our trained model, and this way we can pick up where we left off and resume training or use the trained model for inference whenever we want. And finally, we'll evaluate and test our trained model. We'll see how it performs in the game environment and analyze its decision-making capabilities. Okay, we are going to start by creating our project folder and by installing all the necessary dependencies to train the model on and to run it in the browser. And we are going to clone from GitHub the Chrome dino game. And then we are going to create the first file, which will be Chrome game proxy, where we'll be able to simulate few game functions and make sure our model can interact with a game. So first I'm going to make directory dino player, then cd into it and open it in the Visual Studio Code. Okay, go to command line and I'm going to do sudo npm init and y. Okay, we have the JSON package.json now, and we want to install a few things. First, I would like you to install npm install globally HTTP server. This will be used to run our game on localhost. I already have it installed, but if you don't have it installed, just install it. Or if you want to use some other type of server runner, you can use that also. It's not a big deal. Okay, and now we want to install other dependencies that are necessary for training the model and running the game. So first one will be tensorflow/tensorflow.js, then tensorflow/TF.js node, since we are running it in node, then colors for colorful console logs, and puppeteer for running it in the browser. Okay, let that install, and now after that we want to git clone the repository of the dino game, and here I need to do sudo. Okay, and now let's after this is done, we want to clone the directory of the game. So maybe I should do it on the new command line. So I'm going to navigate to this folder. Okay, and do sudo git clone https://github.com/trexrunner.git. Okay, want to clone that, and we're going to run the game by going into this directory and doing HTTP server. Okay, so like this, cd trexrunner and do sudo HTTP server here, and it will run the game. So if you go to the port, it will be able to play the game. So here, copy this and you can play the game if you want, but we don't want to do that right now. Okay, here it installed all the necessary packages, and now let's go to our Visual Studio Code, and here let me just close this, and here we want to create new folder called source. Inside of that we'll have few files, but first one will be game.js, and here I want to create a class called Chrome Game Proxy, and essentially this class will be just imitation of the game. So constructor page, and this will take the page that we are on, and this page is equal to page, this in jump will be equal to false, and this in duck is equal to also false. Okay, and here we'll have few functions like jump, duck, and stand, and state that we can return the current state of the game, and then we are going to export this. So the next function will be async jump. Here we are going to do if this in duck. So if currently it is ducked, if the dino is ducked, we want to do await this page dot keyboard up and do arrow down. So this is the command to press down, and this in duck is equal to false. And if is not this in jump, so if it's not jumping, await this page dot keyboard down space. So we are just imitating what we would do if we are playing the game in real life. So jump, okay, and then we are going to do async duck. If this dot in jump, and we are going to do await this page dot keyboard up space, and this in jump is equal to false, and then we are going to do if not in this dot in duck. So if it's not ducking, await this page dot keyboard dot down arrow down, and we are going to do this in duck is equal to true. Okay, so the next method will be stand. Async stand function will be, we can just copy this, let's do it like this. Okay, if this in jump, we are going to do this page keyboard up and space, this in jump stays false, and if this in duck, away this page keyboard up arrow down, this in duck is equal to false. Okay, the next method, so these are the methods for jumping, ducking, and standing. You know, the standing is the default state of the player. Then we have async state method, which will be return await this page dot evaluate. Then we are going to do callback, and here I is equal runner dot instance. Runner is the class of the player. So if you're playing the game and you type in runner.instance, you'll receive the player info, actually dino info. So yeah, that is the runner, and we are going to return here speed is equal to i.current speed. That is the info that we are getting from a game. Jumping is equal to i.trex and jumping. So these are all the properties that we are getting from the game instance of our player. Y position is equal to i.trex dot y position. Done is equal to i.crashed. So this will be true if we crashed into cactus or a bird and the game is done. Then we have obstacles. Obstacles is equal to i.horizon. dot obstacles time is equal to I dot time. Okay, and you can check all these properties if you go to the game and do console log to inspect the state of this. And obstacles, these are the obstacles like cactuses, birds, and these will be used to take into consideration when we are predicting the next move. Do we want to duck, jump, or stand? Okay, async state, then we have restart. Okay, async restart. So this is for restarting the game. For example, when we are training the model and we crash, we want to restart right away so it trains the next iteration. So this page dot evaluate, and we'll have callback here also. Okay, and here we're going to do runner dot instance dot t-rex dot exposition will be 50. Why 50? Because I think we found there is a bug in the game, or for some reason in our code exposition increases over time as the model goes over, and for some reason it starts from bigger exposition every time, so it doesn't train correctly. So this is just a default setup we are doing to set it to 50 every time we restart the game. So it could be bug with the game, it could be bug with our code, but this is just something to prevent it. Okay, runner dot instance again and do restart. Since this option also has restart, this is just a wrapper function, so the instance already has a restart function, but we just want to make sure it starts always from the same position, so we are adding a wrapper around it. Okay, async perform action. Here we'll have action. Okay, and we're going to do switch action. Case 1 is equal await this dot jump. So action 1 will be jump. Then we have break. Then case 2 will be await this duck. So this duck and break, and the third case will be 0 and also have default await this stand. So default will be stand because that is the default when we start the game. So if there are no obstacles, there is no reason to jump or duck, so that is the default behavior. Module.exports is equal to Chrome game proxy. Okay, so this is it, and this is the first file. Now it's time to create next file, and it's memory.js. So in source folder, do memory.js, and this will be the class, which is a data structure used to store and manage the agent's experiences during training. So do class memory. Here we are going to have constructor, and inside of that we'll have buffer size, then epsilon, which will be equal by default to 0.01, alpha, which will be equal by default to 0.5. Then here we'll have this buffer size will be equal to buffer size, and this is we are here setting the maximum size of the memory buffer. Then we'll have this buffer, and it will be equal to new array. We'll have buffer size dot fill null. Okay, and we are here initializing the memory buffer with null values. Okay, next we'll have this dot pointer is equal to 0, and this is the pointer to the current position in the buffer where the next experience will be stored. Then we'll have this dot count, and it will be equal to count of the total experiences currently stored in the buffer. Then we'll have this sum priorities, priorities is equal to 0, and it will be sum of all the priorities of all experiences inside the buffer. And then we'll have this epsilon will be equal to epsilon, and here we'll have a small value to ensure that no experience has a priority of 0. Then we'll have this alpha will be equal to alpha, and this is the exponent for priority calculations. Then we'll have this priorities, and it will be new array of buffer size and fill width 0. So this will be an array to store the priorities of experiences in the buffer. Okay, this is the first method, actually is the constructor. Then we have add method, add experience. Okay, this will be used to add to store new experience in memory buffer for every cycle. So with this buffer, this pointer is equal to null. So if it doesn't exist, so if it's empty value, this count plus plus, so count increments, and we are here incrementing the count of total experiences if a new slot is being filled. Then we'll have const old priority is equal to this dot priorities, this dot pointer. Okay, and here we are getting the old priority of the experience at the current pointer position. Then we have const new priority is equal to 10, and here we are setting a high initial priority for new experiences to ensure they are sampled at least once. And then we have this sum priorities is equal to this dot sum priorities plus new priority minus old priority. Okay, and here we are updating the sum of priorities. Okay, and then we have this priorities is this pointer at the pointer location is equal to new priority. Okay, and here we are updating the priority of the experience at the current pointer position. Then we have this dot buffer, this dot pointer is equal to experience. Okay, and here we are storing the new experience at the current pointer position, and then we have this pointer is equal to this dot pointer plus 1 do module this dot buffer size. Okay, and here we are incrementing the pointer. Okay, so that is the add method. Now we want to add sample. Sample we have batch size and priority scale, which will by default be equal to 1. And this is used, so for example, the sample method randomly samples a batch of experiences from the memory buffer based on their priorities. So here we are going to do priorities, and it will be equal to this dot priorities dot map, and here we are going to have p which stands for priority math dot power p to priority scale, which will be 1 by this sum priorities. Okay, and this calculates the scale priority of each experience. Then we'll have const cumulative probabilities is equal to new array of this dot buffer size, and we are going to fill it with zeros. Okay, so this initializes an array to store cumulative probabilities, and then we are going to have cumulative probabilities at position 0, the equal priorities at position of 0. So we are setting the first value in cumulative probabilities array, and here for let I is equal to 1, since we already assigned at position 0. So here we have this dot buffer size, and we'll have I plus plus and cumulative probabilities will be of I will be equal to cumulative probabilities of I minus 1 plus priorities of I. Okay, and then here we are calculating cumulative probabilities. Then we are going to have samples, which will be equal to our empty array, and we are initializing an array to store sampled experiences. Okay, and then we have const sample indices is equal to an empty array, and here we are initializing an array to store the indices of the sample experiences. So for here we're going to have let I is equal to 0, then I is less than batch size, then we are going to increment I, then we are going to have const sample probability is equal to math.random. So we are just generating a random number for sampling, and here we are doing sample index is equal to this dot binary search, and we're going to have cumulative probabilities and sample probability. And binary search we haven't created yet, but it'll just be a regular binary search. We are going to add that after this method, and here we are just finding the index of experience to be sampled. Okay, then const experience is equal to this dot buffer at sample index. Okay, and we are getting the sample experience here, and then samples dot push experience. So we are storing this sample experience, and sample indices dot push sample index. Okay, storing, so here we are storing the index of the sample experience, and then after this for loop we are going to do return samples sample indices. So that is what we are returning here, and we have two more methods to add to this class. And first is binary search, so it will be a regular binary search. And if you don't know what binary search does, it's the method that finds the index of value in a sorted array using the binary search algorithm, which we'll create right now. Okay, array value let start is equal to 0, so we are initializing the start of the search range. Let end is equal to array length minus 1, so that is our range. And while start is less than or equal to end, we'll have const mid is equal to math floor start plus end and divide by 2. So we are here calculating the midpoint of the search range, and if array position mid is equal to value, we are going to return mid. So if the value is found, we are returning that index. Else if array of mid is less than value, here we are returning start is equal to mid plus 1. So if the value is greater, we are going to update the start of the search range, and then else end is equal to mid minus 1. So if the value is smaller, we are updating the end of the search range, and after the while loop we are returning start. Okay, and then the last method in this class will be update priorities. Priorities. Okay, sample indices and priorities, and for let I is equal to 0, I is less than sample indices dot length, and we'll have I plus plus. Const index is equal to let's do sample indices at y at I, and here we are getting the index of the experience that we want to update, and here we have old priority is equal to this priorities at index. So we are getting the old priority of the experience, and then we have const new priority is this dot actually math dot power of priorities at I plus this dot epsilon and this to this dot alpha. Okay, and I figured out I spelled alpha wrong, so let's rewrite that everywhere. So alpha here, and here also. So it was a spelling mistake. So we are here we are calculating a new priority of the experience. These priorities at index will be equal to new priority. So here we are updating the priority of the experience, and here the sum priority is equal to this dot sum priorities plus new priority minus old priority, and this is the way we are updating the sum of the priorities. And then we are going to do module.exports is equal to memory, and that is our memory class. And we have to create advantage normalization, so that is the custom layer that we are creating, and after that we are going to create our training and playing setup and add it to the main file, and we'll be able hopefully to run this model and start training. So now it's time to create an advantage normalization class which will extend TensorFlow layer. So it is custom layer that we want to create. So here we are going to do advantage normalisation.js, and here we are going to do const TF is equal to require at TensorFlow TF.js node. Okay, class advantage normalization extends tf.layers.layer. This is the custom layer, and because it's not available in TensorFlow.js right away, we want to create it on our own. And here we have static class name is equal to advantage normalization, and this is required as a static property in order for custom layer to work. Then we're going to have constructor which will be empty, and just call this super here with an empty object, so it is taking default params. Then we are going to create method for computing the output shape of the layer based on the input shape, and here we are going to have const compute output shape, and it will take input shape as param, and then we are going to do return input shape of 1. So advantage normalization layer receives two input tensors, one of the shape null 1 and y, and one of shape null x and y, and this reduces to one output tensor of shape null x and y. So this is the final tensor, and here we are returning the shape of the second tensor. Okay, and we want to have method call inputs, so it's taking inputs, and this is just to perform the forward pass of the layer, and we are going to have return tensorflow.tidy, going to receive a callback, and here we're going to have const val is equal to inputs of 0. And before we continue, TensorFlow.id is used to free any intermediate tensors created during this method. So it's just to prevent memory leaks. We're going to end with val. We are extracting the first input tensor, so value tensor, and then we have advanced inputs is equal to 1. Extract the second tensor, so advantage tensor. So first one is value tensor and the second one is advantage tensor. Const mean is equal to TensorFlow mean advantage 1 and through. So here we are computing the mean of the advantage tensor along axis 1 and keeping the dimensions. So here if you hover mean, you can get the explanation of what it does. Then we have const centered is equal to advantage.sub mean. And here we are subtracting the mean from the advantage tensor to center it. Then we are returning centered add val. And here we are adding the value tensor to the centered advantage tensor and returning the result. And the last method we'll need here is get class name also. This is just for custom layer to work. So here we are returning advantage normalization. And we want to do one more thing, TF serialization.register class, and we'll take the name of the class. And this is also just necessary for custom layer to work. So module.exports is equal to advantage normalization, and that is our custom layer that will help us with training the model. Now it's time to create model actions file where we'll have our logic for training the model and adding the playing mode. So in source, create model actions.js, and we are going to start by importing TensorFlow. So require add TensorFlow/TF.js node. Then const puppeteer is equal to require puppeteer. Then colors will be equal require colors. And for our console logs, then const file system is equal to require file system.promises. Const memory is equal to require memory. Then const Chrome game proxy is equal to require game mock. Then we want to do const is equal to require advantage normalization. Okay, and we are going to also call the import advantage normalization. Then we are going to start by writing some functions that will help us. So first function will be function KL divergence. It will take y through and y pred. Now what this function does is it's computing the callback Kleibler divergence between two probability distributions. So we are going to do return TensorFlow tidy here, and first we are going to do const y through clipped is equal to TensorFlow clip by value y through 1e minus 7. So this is the exponential number, and here we are clipping the y through and y pred values to avoid division by 0 and logarithm of 0 issues. So y pred clipped is also the same value. Then we are going to have const division is equal to y through clipped division y pred clipped. Okay. Then we want to take the logarithm, so log div is TensorFlow logarithm of division. Then const kl div is equal to log div multiplied by y through clipped and sum by -1. So we are multiplying log div with y through clipped and summing over the last axis to get the KL divergence. And here we'll return KL div. Okay. Next function will be sum KL. We'll have y through and y pred also, and we are going to return KL divergence y through y pred and then sum it up with -1. So that means we are summing it over the last axis. Then we'll have function clip. It will take v, min, and max. And this function clips a value v between a minimum and maximum value. So we are going to do return math.min, math max, v min, and max. Okay, after that we want to create class dino agent. Here we'll have constructor and it'll be proxy. We'll have this dot proxy is equal to proxy. Then this memory is equal to new memory of, let's do 100,000. That'll be our buffer size. Then this batch size will be 32. And then this comma is 0.9. So this count factor will be between 0 and 1. So we are choosing 0.9 here. Then this target update frequency is equal to 1280, and this is how often to update the target model, and it must be the multiple of the batch size. Then exploration, this epsilon is equal to 1, and this epsilon decay is equal to 0.01. So that is the rate of exploration to exploitation. Okay, then we'll have this dot steps is equal to 0. This multi-step is equal to 3. So this is the number of steps used internally to regulate training and target model updates. Then we are going to have distributional DQ and related values. So this dot d atoms is equal to 51, so that is the number of atoms. Then this dot v min is equal to -5, so this is the minimum expected reward. And this dot v max is equal to +5, actually it has 5, and that is the maximum expected reward. This dot delta underscore z is equal to this v max minus this v min divided by this the atoms minus 1, this dot z is equal to an empty array, and for let I is equal to 0, I is less than this dot d atoms I plus plus, this dot z push this dot v min plus I times this dot delta z. Okay, this is our constructor. Then we'll have a method called obstacle to vector. It'll be obstacle vector and offset. We'll have const distance is equal to math.min 39 math.max 0, and here this operator will have obstacle, then x position minus 19 and divided by 16. So here we have minimum distance of 19 and maximum distance of 625, and we want to convert the instance into integer from 0 to 39. Okay, then we'll have a vector of offset plus distance will be equal to 1, and vector of offset plus 40 will be equal to obstacle dot x position, and vector of offset plus 41 will be equal to obstacle dot width, and vector of offset plus 42 is equal to obstacle dot size. That is our obstacle to vector method. Then after that we want to have the state to vector. Here we'll have state as an input, and we'll have let vector. And here we'll have an array of zeros. So we could have like actually new array of 89 and fill it with zeros. Then we'll have const obstacles is equal to state dot obstacles. Okay, if obstacles dot length is bigger than 0, we'll have this obstacle to vector obstacles of 0, a vector, and 0. And if obstacles dot length is bigger than 1, we're going to have this obstacle to vector obstacles of at 1 vector then 43. Okay, after that we want to decide, do we want to jump yes or no? So if state jumping, we'll have a vector of at 86 will be equal to 1, and then vector of 87 will be state dot y position, and let speed is equal to math dot min 17 math dot max. here we'll have 0 math dot round state speed -6, and then we'll have vector of 88 plus speed is equal to 1, and we are going to return vector. Okay, that is our state vector method. Then we want to add delay method that will help us with delaying the time when we need to do it. So return new promise that will have resolve and set timeout resolve time. And after that we'll have the method to update the target's model weights with the online model weights. So async update target model, and it will be const online weights is equal to this online weights online model actually get weights. Then we are going to do await this dot target model dot set weights online weights, and then we are going to do await this dot target model save, and we'll have file so it knows it's on our file system, and path, so I'll have dino crom model / target, and this will update the file contents of this path. Before we continue, I'll figure out this new array in state vector needs to be 106 instead of 89. Okay, now let's continue with async train model, and it will be big function here, but with episodes. We'll do fs append file logs.txt, and we'll do new line, and just here this is just for us to know in our logs this is a new session of training, and here we'll have catch error. There is an error. We are going to do console.error failed to write logs.txt, and then error message. So this is just for login. Then we are going to have let high score is equal to 0. So this is the variable to keep track of the high score across episodes. Then we are going to have for let episode is equal to 0, episode is less than episodes dot length. Actually just episodes, not length. And then we have episode plus plus. Let episode reward will be equal to 0. So this is the variable to accumulate the total reward for the episode. And then let episode steps is equal to 0, and this is the variable to count the steps taken in the episode. And then we are going to do await this dot proxy dot restart, then await this dot delay 100 milliseconds. So we're just giving game time to settle, and then we are going to do await this dot proxy dot jump, so we kick off the game again. Then let state is equal to await this proxy dot state, so we are getting the initial state here, and then we are doing multi-step buffer is equal to an empty array. So this is the buffer to store multiple steps for n-step queue learning. Okay, after that, what we want to do after this for loop is have a while loop, which will be while state dot done. While state is not finished, actually while the game is not over, we're going to do const state vector is equal to this state to vector method that we defined before in state. So here we are converting state to a vector. Const action is equal to this select action state to state vector, and here we are selecting the action based on a state, and this proxy perform action, and we are passing the action. So here we are performing the selected action. If episode steps is bigger than 10,000, console clg, we are going to console log this dot proxy dot string. Okay, now after that, episode steps, and after that episode steps. Okay, and yeah, this while loop should have been inside the for loop. I accidentally put it outside, so I saw episode steps was undefined. Okay, it should be inside. Now we logged this. Okay, the next thing we need to add another if statement. So if this dot memory dot count is bigger than or equal to batch size, we want to do await this dot optimize model, and here we need some time to pass, otherwise the next state will be too close to the current state and the model won't see the result of its action. So instead of sleeping, we can do the optimization here, and this will take some time. So okay, then we are going to do let next state is equal to await this dot proxy dot state, and while next state done is not through and next state time is through then we are going to have state dot time less than 30 seconds and await this delay 5, and next state will be equal to await this dot proxy dot state. So here Chrome game seems to use 60 frames per second, so time in game passes in steps of about 16 to 17 milliseconds, and we try to use 30 frames per second, so we wait here until 2 time steps about 30 to 40 milliseconds pass. Okay, after that I want to calculate const time delta is equal to next state dot time minus state dot time, and here we are calculating time difference between states. So if time delta is bigger than 40, we are going to do console.warn time delta bigger than 40 milliseconds, and then plus time delta. Okay, then we are going to do else if time delta less than 30, and here if not next state dot done, we are going to do console error, and here time delta less than 30 milliseconds and not done failed delay. And we can do plus time delta. And here the result should not happen, because that means that delay method failed for an unknown reason, but yeah, that shouldn't happen. So here else we'll have if multi-step buffer dot length is bigger than 0, we are going to do const last is equal to multi-step buffer and multi-step buffer dot length -1, and last dot done is equal to true, last dot reward is equal to -1, while multi-step buffer length is bigger than 0. We want to do this dot multi-step and multi-step buffer, pass it here. So here in this else statement, and let's do just else here so I can explain everything. So console warn lost terminal state due to missing multi-step buffer. So here terminal state in this else statement was reached in less than 30 milliseconds, and to not lose the result, we assume that this is the late result of the former action. So last action is updated, and this only works with multi-step buffers. So here else if, and after that we want to have another else, just a regular else, and here we'll have const next state vector is equal to this dot state to vector next state, and let reward is just just leave it like this, and if next state done, we are going to do reward is -1, so we are basically punishing the model. Then else if action is equal to 1, reward is equal to 0, and episode steps increments. And here we are experimenting, so making jumps expensive to avoid random jumps. So we don't want it to jump when it doesn't have to. And reward here in other cases will be 0.1. So because it stayed alive, it figured it out properly, so it did a good thing, and episode steps will be incremented. Then we'll have episode reward will be plus equal to reward. Multi-step buffer, we are going to push an object state will be state vector action reward, next state will be next state vector, and done will be next state dot done. Then we'll have if next state dot done is true, while multi-step buffer the length is bigger than 0. We're going to have this dot multi-step and pass the multi-step buffer. So here we are going to flush multi-step buffer to replay buffer. And else if multi-step buffer dot length is equal to this dot multi-step. It will be this multi-step and pass the multi-step buffer also. And here we are adding one step from multi-step buffer to replay buffer. Okay, and here we'll assign state is equal to next state. So here we are updating the state for the next iteration. Then here we'll have this dot epsilon is equal to math.max. We'll do this dot epsilon minus this dot epsilon decay, and the second argument will be 0. So here we are updating the exploration rate. High score will be equal math dot max, high score, and episode steps. So here we'll update the high score if it's necessary. Then we are going to do console log, and let's do template log. So episode, and here episode done, score is episode steps. We are going to do high score. Then fs append file logs.txt episode, so episode +1, and total reward. Actually, let's do it here. Total reward will be episode.reward. Then catch error, console.error, failed to write to logs.txt, and error.message. Okay, that is our method for training the model. Then we'll have multi-step function. Multi-step buffer will be an argument, and here we'll do let r is equal to 0. So here we are calculating the multi-step reward by summing up the reward of each step, discounted by gamma raised to the power of the step index. So here first we are initializing the cumulative reward to 0, then we are going to do for loop let I is equal to 0, I is less than multi-step buffer dot length I plus plus, and here I plus equals to math dot power of this dot gamma of I times multi-step buffer of I dot reward. Okay, and here we are accumulating the discounted reward. Then we are going to do const first is equal to multi-step buffer at 0 index. So here we are getting the first step from the multi-step buffer. Then const last is equal to multi-step buffer dot length minus 1, getting the last step from the multi-step buffer. Then this memory dot add state is equal to first dot state action, first dot action reward is equal to r, next state is equal to last dot next state, done is equal to last dot done. So here we are adding a new experience to the memory with the cumulative reward and adding the state and action from the first step and the next state and down flag from the last step, and then multi-step buffer, actually just multi-step buffer splice 0 to 1. So here we are removing the oldest step from the multi-step buffer as it had been used. Now it's time to create optimize model function. So here async optimize model, and we'll do if this dot steps module this batch size is not equal to 0, we are going to do this steps plus plus return. So here this condition ensures that the optimization is performed only once every batch size steps for performance reasons. Then we want to do const the structuring of samples and sample indices is equal to this dot memory dot sample this dot batch size, and here we are sampling a batch of experiences from the memory. So const states vectors, here we are going to do samples dot map s and return dot s state, then do const next state vectors and states next states vectors, and samples dot map s to s dot next state. Then we are going to do states tensor is equal to TF tensor 2D states vectors. Then we are going to do const next states tensor is equal to TF tensor 2D, then next state vectors. So here we are speeding up and making the predictions of full batch. Then here we are going to get Q value predictions for current and next states from both the online and the target models. So here online model Q values tensor is equal to this dot online model dot apply states tensor. Then we are going to do const online model next Q values tensor is equal to this dot online model dot apply next states tensor. Then we are going to do const target model next Q values tensor is equal to this dot target model dot apply next state tensor. Okay, after that we want to convert tensor to JavaScript arrays for further processing. So here const online model Q values is equal to online model Q values tensor dot data sync, and const target model next Q values is equal to target model next Q values tensor dot data sync also. Then we want to do const number of actions is equal target model next Q values tensor.shape at 1, and then we want to do const number of atoms per sample is equal to number of actions times this dot d atoms. Okay, and we want to define some variables here. td error sum is equal to 0, let td error terminal sum is equal to also 0, and let terminals count is also equal to 0. Okay, now after we've done this, we want to do now, let's go first over what's DQN. So DQN, we have target model where, and it is used to select action, and its prediction is used to updated value. And double DQN, we are using online model to select action, but still target models Q value prediction is used as updated value for online model. And with distributional DQ network, we have predictions are not values but value distributions, and TD error is set to categorical cross entropy loss between predicted distribution and updated distribution. So here online model next Q values tensor has shape of 64, 3 and 51, and we multiply by z in axis 2, sum up in axis 2, and argmax in axis 1. So we are going to do that by doing t1 is equal online model Q values tensor multiply this dot z. Then const t2 is equal t1 sum, and passing the 2 as an axis, and const t3 is equal tf arg max. We are passing t2 and axis 1. Then we have const next actions is equal to t3 data sync. Then we'll have let priorities is equal to an empty array. Then we are going to do for loop is equal let I is equal to 0, I is less than this dot batch size I plus plus, const r is equal to samples I of reward, then const action is equal to samples I at action, then const terminal is equal to samples I dot done, then const next action is equal to next actions at I, const p is equal to target model next Q values dot slice. Here we are going to do I times number of atoms per sample, then next action times this dot d atoms, and then I times number of atoms per example plus next action plus 1 times this dot d atoms. So it's the same as previous, just plus 1 next to next action. Then here we want to use categorical algorithm, and we are initializing an array m to store the updated probabilities mass function. So we are going to do const m is equal to an empty array. Then we are going to have let n is equal to 0, n is less than this dot d atoms, m plus plus, and then m at n index is equal to 0, and then we are going to do for let j is equal to 0, j is less than this dot d atoms, j plus plus, And here we are computing the projection of TF.js on the support Z. So here we are going to do let and assign. So here if terminal TZJ, and here if terminal doesn't exist, we're going to do TZJ is equal to clip r plus this gamma times this dot z at j, this dot v min, and this dot v max. So here, if there is no terminal state, we are calculating TZJ using the Bellman equation. Else, if terminal states exist, the reward R is the final value. So TZJ is equal to clip R, this dot v min, this dot v max. Okay, after else, we are going to have const bj is equal to TZJ minus this dot v min divided by this dot delta z. So here bj is the normalized and shifted value of TZJ. And then we are going to have const L is equal to math floor of bj. So L and U, let's do U also. Here math dot seal bj. So L and U are the lower and the upper bounds of the index and the support. So after U, if L is equal to U, we are going to do U plus equal to 1. Then M at the L index plus equals P of J times U minus Bj. M at U index plus equals P at J times Bj minus L. So here we are distributing the probability mass of atom J between indices L and U in the updated PMF, and this is done according to the proximity of Bj to L and U. After that, we want to do const index is equal to I times number of atoms per sample plus action times this d atoms. Then const original distribution is equal to online model q values slice. Here we are going to do index plus this dot d atoms, and here we want to do TD error, and TD error is KL divergence between target and the original. So const TD error is equal to TF tidy KL divergence TF dot tensor M and TF dot tensor original distribution and data sync at 0. Then we are going to reintegrate target values into online model Q values. So for let I is equal to 0, actually not y but n, and n is less than this dot d atoms n plus plus online model Q values index plus n is equal to m at the n position, td error sum plus equals to td error. If terminal exists, we're going to do td error terminal sum plus equals to td error terminal count plus plus, and then we are going to do priorities push td error. Okay, after that's done, we have a few more things to do. So CLG, let's console log what we have so far. Average td error will be equal to td error sum divided by this batch size. Terminals only will be equal to td error terminals count divided by terminals count. td terminal sum. Okay, td error sum divided by this batch size. Terminals only will be td error terminals sum. Okay, that is our console log. And then we are going to set td error as new priority for the samples in the memory. So this dot memory update priorities sample indices and priorities. Then we are going to do const target tensor is equal to TF tensor 3D online model Q values, online model Q values tensor dot shape, and here online model I said mode instead of model, so let's fix that. Model here. Okay, model, and here also model. Okay, target tensor. Then we want to do await this online model dot fit states tensor target tensor, and here we are going to have a config. So epochs will be 1, batch size will be, I don't know why it's setting this, we don't need this. Batch size will be this dot batch size. Shuffle will be true. Verbose will be false. Okay, and now we want to update the target model's weight periodically. So if this dot steps module this dot target update frequency is equal to 0, I'm going to do console log updating the target's model. Await this update target model. Then states tensor dispose. I want to expose 6 tensors here, so states tensor. Then next states tensor, target tensor, then online model Q values tensor, online model next q values tensor, and target model next q values tensor, and I want to do this steps plus plus. So that is our optimize model method. Next method is create model, and let's create it. Create model. Here model is distributional dueling double DQ network. So if we had two branches, one for state value distribution, which we'll call V, and one for advanced distribution, A value distribution has shape 1 and D atoms, and advanced distribution has 3 and D atoms. Number of atoms usually is 51 by C51 model, and both branches are recombined into a single distribution Q with shape 3 and D atoms. So let's start. Const I is equal to TensorFlow input, and here we have object with shape of 106, name is state input. Then we'll have const cd1 is equal to TensorFlow layers dense units 64 activation ReLU and name will be common dense 1. Then we'll have cd2 units 64 activation stays the same, but name will be common dense 2. Then we'll have to break up into two branches. So const x1 is equal to TF layers dot dense units 64 activation ReLU and name will be vdense. Then const x2 will be TF layers dense units 64 activation ReLU and name will be a dense. And also I forgot here vdense apply cd2, and here I'm going to do apply cd2 also. Then const vflat is equal to TF layers dot dense units will be this D atoms, activation will be linear, name will be flat v, and apply to x2. Actually v flat is x1. Okay, now we want to reshape v to dimensions 1 and D atoms. So const v is equal to TensorFlow layers reshape target shape t this dot D atoms, name will be reshaped v apply v flat. Const a flat will be TensorFlow layers dense units 3 times this dot D atoms, and activation will be linear, name will be, so here we are doing a flat, so we are going to name it flat a, and apply x2. Then we are going to reshape A to dimensions 3 in the atom. So const A is equal to TF layers reshape, and here we are going to do target shape 3 this the atoms. Then we are going to have activation of linear, and actually not just, we are going to have not activation but name will be reshaped A. Okay, and we'll have to apply here a flat. Now we want to do merged, so remerge with lambda layer, so new advantage normalization, and do apply V and A. Shape of merged data will be const output will be TF layers soft max, axis will be 2, name will be soft max distributions. Okay, and now we want to create a model, so const model is equal to TF model optimizer will be TF train Adam 0.000125. That is the best rate we found for our solution. So loss will be sum KL, and we are going to return model. And sum KL is what we've defined this function here. Okay, that is our model for our method for creating the model, and last method in dino agent class will be select action state. Here const r is math.random. If r is less than this dot epsilon, we are going to do return math floor math random times 3, return TF tidy, and const state tensor will be equal to TF tensor to the state and array of 1 and 106. Then we'll do p this online model apply state tensor. So here we are choosing the best action according to the model, and then const q is equal to p dist multiply this.z sum with 2, and then const action is equal to TF argmax q and 1, and we are going to return action data sync of 0. So here with q, pdist is per action probability distribution over possible rewards with shape of null 3 and 51, and q with shape of s and a value is sum of z times p at index I, and shape will be null and 3. Now let's write a function for launching a browser. So async function launch browser will be const browser is equal to await puppeteer launch. And here we are going to do headless is false because we want to see how it trains, and args will be mute audio because I don't want to have that annoying sound that in the game, so I want to mute the audio. Const space is equal to await browser new page. We're going to do await page go to HTTP 127.0.0.1 and port is 8080, so that is the place where we are running the game on our local host. Then async function create Chrome game proxy. We're going to do const page is equal await launch browser, then await page, wait for function runner dot instance underscore is not equal to undefined, then return game proxy is equal to the new Chrome game proxy with the page instance. Okay, and we have function compile model is taken as an argument, and we are going to do model compile optimizer, which will be TF.train atom 0.000125, and loss will be sum KL. Okay, now you have two more functions for setting up the model training and playing mode. So here async function setup model training will be const game proxy is equal to await create Chrome game proxy, const dino agent is equal to new dino agent game proxy. And then we are going to try to load the saved model if it exists. Okay, try dino agent dot target model is equal to await tf load layers model from file dino chrome model slash target slash model.json. Then compile model pass the dino agent.target model, then console log loaded saved model.green. It's just the add up that we got from colors package. Dino agent epsilon is equal to 0. So here to see the effect of loaded model, set epsilon 0 to be greedy, and otherwise model will fail fast due to epsilon is equal to 1. So that is the range from 0 to 1, but here we are setting it to 0. Console log here, no saved model found, creating a new one. So if we don't have anything saved, this will be the first time. And here dino agent target model is equal to dino agent.create model. Okay, dino agent.online model is dino agent create model, and dino agent online model set weights to dino agent target model get weights. We're going to do compile model dino agent online model, and const episodes is equal to 100,000. Await dino agent train model episodes. Okay, so here we are starting to train our model, and we have one more function, which will be, I would suggest just copy this function and we can go based on this. So set up model plane. We are creating a game proxy dino agent. We are trying to load the model, compile the model dino, and okay, this stays the same. No save model found here, and we are going to set red. And we're going to say you need to train the model first, and we are going to do process exit 1 because we don't have anything, so it can't play. Okay, dino agent online model is equal to dino agent create model dino. We are setting the weights, compiling the model. Okay, and okay, we are compiling the model. Now we want to do await game proxy restart. So we want to restart the game, await dino agent dot delay 100 to settle the game, await game proxy dot jump, so we want to start the game. Okay, let state is equal to await game proxy dot state, getting the initial state, and while through, so infinite loop, const state vector is equal to dino agent state to vector state, pass the initial state, and const action is equal to dino agent select action and state vector. So it decides what it wants to select. Then game proxy perform action. Then we got from the prediction, and let next state is equal to await game proxy dot state, while there is no next state dot done and next state dot time exists minus state time is less than 30 milliseconds. Await dino agent delay 5, next state is equal to await game proxy dot state. So we are getting the new state here. State is equal to next state if state dot done. We want to do just copy this code, restart the game, delay 100 jump, and state is equal to await game proxy dot state. So we are getting the new state here. Okay, that is our model actions file, which is pretty big, but we are almost done. We just need to create dino bot.js too, and we need to export this also, I forgot. So here I'll do module.exports is equal to setup model training and setup model playing. And now we want to go to dino bot, and here we are going to do const colors is equal to require colors, const setup model training, setup model plane is equal to require src / model actions, and here I'm going to do async immediately invoked function expression args is equal to process dot argv dot slice 2 if args includes train. We're going to do await setup model training, else if args includes play, await, set up model plane, and else if nothing is passed or if the wrong command is passed, we are going to do console log, please provide an argument here train dot yellow, or going to do play also dot yellow, and process exit. So that is our model, and now we are going to start training. Before we run our code and start training, I figured out there are some bugs. So here on line 12 it should be y pred instead of y through, and on constructor instead of multi-step it should be multi-steps. Then in our create model function also there should be apply of I, and here apply of cd1. Okay, and here shouldn't be like this, should be an array as an argument. Okay, const, and make sure this here model is equal to TF model, inputs is I, outputs is output, model compile with this. Also make sure that is fixed. And now go to command line, run cd into T-Rex runner, do HTTP server, and here want to run the dino bot with train command. Okay, and as you can see it's exploring. Right now it's trying different docking, standing, and jumping methods, and you can see here on command line episode 1 done and episode 2 done. So yeah, you can see the score, everything is logging, and if we leave it like this, wait till it's done with the session, it will save the weights to the file, but I don't want to wait for that now. And we can't run it in the play mode right now because we don't have it, but in the logs file you'll be able to see all the logs. And if you want to try out the model in the play mode, you can download it from the GitHub, from the repo, because that's where we trained it, and it's not performing perfectly. The biggest score that we achieved was about 6,000 points. It usually scores about a few hundred points, but yeah, it needs improvement. And if you have any suggestions and want to work on this project, just let me know, and you can maybe do even pull requests on GitHub. So yeah, that's it.